Good evening, all. I am Lakmal Isuru, the chairman of Building Service Engineering Sectional Committee. So, on behalf of the Building Service Engineering Sectional Committee, so we all warmly welcome our distinguished speaker, Engineer Chandana Dalugoda, as well as the participants who join online with us. We have almost 61 participants with us at the moment. So we expect 100 plus participants. Surely it will be there during the webinar session. So we'll starting from now the session 2023-2024. Our webinar series will start from here. This is a webinar number 1. Talking about the Building Service Sectional Committee, it is one of the main dynamic active sectional committee in the ISL who in combination with all mechanical engineers, electrical engineers and civil engineers, so who are practicing the building service engineering in the industry have joined with us. So and we are serving the better service to the industry as a building service discipline. So the air conditioning is one of the key and main sub-discipline out of the building service engineering. So the energy is the vital word with us with compared to building service engineering. So today we'll start this webinar series from the discussion about the energy. So coming back to our today webinar, our topic is the sustainability and the path to zero energy buildings, and building services engineers perspective. It is a time being valued topics for the country like Sri Lanka, because we are now have a good discussion in national level regarding the energy optimization and energy management like that. So this will be the vital and important webinar session, especially for engineers who are practicing this building service engineering, for their knowledge and the career development. So coming back to our today's speaker, Engineer Dalugoda, Engineer Chandan Dalugoda. The Engineer Chandan Dalugoda is a chartered mechanical engineer as well as a certified building service engineer. He is a fellow member of ISL and the member of the ASTRI USA. Further, the Engineer Dalugoda is a member of the Chartered Institute of Building Service Engineers, we call CIPSI, and consultancy engineers in Sri Lanka. Engineer Dalugoda is well-known figure in this engineering field with more than 4 decades of experience of many landmark projects under his belt. He was timely president of the ASTRA Sri Lankan chapter and ASTRA Distinguished Lecturer since 2011. Won the ASTRA Chapter Service Award in 2015, and he was an ASTRA Regional Award Merit in the 2015. He is a distinguished lecturer of ASTRA USA and visiting lecturer of the University of Moratuwa, as well as the University of Technology, ISL, IQSL, and Green Building Council of Sri Lanka. And additionally, he is currently the ISL Council member under fellow category, and also he is our senior fellow member of Building Service Engineering. Without any time consumed, I think Engineer Dalugoda is well-known character in the industrial field. So I warmly welcome and warmly invite Engineer Dalugoda to address the gathering. With that note, I just want to mention that you can keep your questions till the Q&A session. So the moderator will be appeared in the chat in the participants. You can put your questions to the moderator, At the end of the session, he will cover your questions and he will coordinate the speaker to give the better answer. Thank you very much. In the good, over to you.
Thank you very much, Isuru. Very long introduction. Good evening to you, everybody. Thanks for joining us today. We are going to discuss about sustainability. Of course, it is a very stale subject. Everybody talk about sustainability. The way it is going, I think even cricket team might talk about sustainability. But we need to understand what is sustainability and path to net zero energy buildings. That is, we are going to talk and under building service engineers perspective. These are the contents that I'm trying to discuss: net zero energy buildings, sustainability, net zero energy concept, greenhouse gases. I will bring a case study on net zero carbon building, then building service engineers role with use of building management systems to conserve energy. Net zero energy buildings. Now, we are familiar with net zero. Moment we hear net zero, it comes to our mind installing solar PV. And it doesn't mean that is going to be a net zero building. On this photograph, what you can see is the new global headquarters of ASHRAE. ASHRAE is American Society of Heating, Refrigerating, and Air Conditioning Engineers, who produce all the standards, very, very important standards on energy and so forth. They had a headquarters in Atlanta, Georgia, but they moved to a new building that is net zero building to show, you know, that the main headquarters itself is a net zero building. So net zero buildings are designed first significantly reduce energy consumption. That is first aim. Reduce energy consumption. And then to meet remaining loads with renewable resources, ideally located on site, generated from site. Now, these buildings are usually connected to grid as what we do here. But energy reduction, usually we have heard green buildings, heavy. We have heard green buildings. Now, this is going beyond. We'll discuss. Of course, ASHRAE has just published a standard that is standard 228, standard method of evaluating zero net energy and zero net carbon buildings performance. I don't have a copy yet, but now we have a method to see the evaluation. How do we evaluate that the building meets a definition of zero net energy, or where those buildings meet a definition of zero net carbon? Right. Now, with regard to energy efficiency and sustainability, the common word is green buildings. Now, what is a green building? Now, there are no actually so-called green buildings. What we do, a normal building, we convert it to a green building. How? Minimal, we achieve these things: minimal consumption, minimal atmospheric emission, minimal discharge of harmful liquid effluents. Those are things that we achieve. Furthermore, minimal negative impact on site ecosystems, maximum quality of indoor environment. So we achieve energy reduction by way of 30% usually for green building, carbon emissions, water usage, solid waste. These are some of the energy saving, average energy savings of a green building. But when we go to a net zero building, what we do, our energy reduction, so-called 30% of green building, we extend it to minimum 50%. So the primary factor, the building must have energy saving 50% against a benchmark or a baseline building. We are going to discuss in depth how we are going to do this. Let's commence with sustainability. Now, sustainability is defined everywhere, but Ashray defined it as providing for the need of the present without distracting from the ability to fulfill the needs of future. Again, providing for the needs of the present without distracting from the ability to fulfill the needs of the future. That means save and for future use, save. But there are some factors impacting sustainability in the world, like population growth, migration, food supply, disease control and improving standards, energy resources availability, material resources availability and management, fresh water supply. That is one of the biggest problems on earth. Fresh water supply, both potable and non-potable, effective and efficient usage practices for energy, resources and water. Pollution, air and water pollution, solid and liquid waste disposal, in fact, land use itself. These are the factors impacting sustainability. Now, is it a myth? This is net zero carbon buildings? No. It is evident that approaching net zero carbon building is difficult. Yes, it is a difficult task. However, it is achievable. These are the goals. Reduce embodied carbon of the building by selecting appropriate materials with low embodied carbon and effective transportation. Now, carbon, what we have heard in these green buildings, carbon footprint. What is carbon footprint? Carbon footprint is reducing embodied and operational carbon footprint. That is reduction of carbon footprint. Carbon footprint is your building, the embodied carbon and operational carbon footprint for annum in terms of tons of carbon dioxide emissions. So now reduce embodied carbon of the building by selecting appropriate materials with low embodied carbon and effective transportation. We'll discuss in detail. That is, if we buy a load of bricks, now that has embodied carbon, because when it producing bricks, that involved with carbon emission. Transportation also included carbon emission. So that is all embodied carbon. Next item, reduce operational carbon of the building by reducing heat gains. As we know, a building consumes energy. If you take 3-4 story office building, majority of energy use for air conditioning systems in this kind of a tropical humid climate, probably it is a heating, building heating in a cold lead country. Plus the lights, lifts, plug loads, ventilation, so forth, all consumes energy. Now, air conditioning system consumes usually 50 to 60% of the total energy consumption of a building. So, reducing heat gains of the building any block or building fabric is a one key role to save energy by 30% up to 50%. That's why I initially mentioned, when we do a building, construct a building, we convert that building to a green building by one way reducing heat gains, utilizing energy efficient equipment. Another thing, when we use equipment such as small fan, a refrigerator, or to a chiller, we'll have to install energy efficient equipment. To do that, we'll have to follow certain guidelines given by ASHRAE standards. Third one, offset fossil fuel energy. You can't use fossil fuel energy. Offset by renewable energy, similar to solar photovoltaic or wind power. And you'll have to store this energy using batteries. Now that is achievable. This is how we go to zero carbon buildings. As we know, carbon emissions increase global warming. Now that is the key thing. We'll have to reduce global warming. Embodied carbon and operational carbon, two things. So net zero approach needs to address reduction of both embodied carbon and operational carbon in a building. Now this is how a embodied carbon comes into the picture. Say this photograph gives you a energy to dig the raw materials out of the ground in a brick making industry. So you are using machinery that emit carbon dioxide. So this one, energy to shape clay, sand, and water into bricks. Energy to heat and shape blocks and turn them into bricks. Then transportation, energy use at site. Finally, at the end of it, energy use if bricks are wasted and loss of resources if landfilled that you use. So whatever we purchase have embodied carbon. To reduce, what we should do, we'll have to reuse material. We'll have to take reuse materials. At present, embodied carbon only accounts for 11% of global greenhouse gas emissions, that is carbon emissions. Operation carbon, on the other hand, as I told you, refers to all the energy used in managing and maintaining the function of building. It can include heating, cooling, lighting, any other power usage need to run the building. So operational carbons currently accounts for 28% of global GHG. Net zero concept. As per ASHRAE, there are a number of different terms commonly used to describe buildings that achieve a balance between energy consumption and energy production. They are zero energy, zero net energy, net zero energy. And we discussed these things. Action taken to reduce emissions from operational and embodied carbon with residual emissions compensated via compensation activities in the transition to net zero emissions. So the definition finally, an energy efficient building where on source energy basis, the actual delivered energy is less than or equal to on-site renewable exported energy. So you would see, we'll have to produce our energy at site in the building. Now we need a lot of PV. To reduce that action, what we should do, we have to conserve energy, then amount of PV usage also reduce. Not even that, solar PV cannot use during night. So we'll have to have energy storage. Carbon capture is another way of reducing carbon emissions to atmosphere. This refers to change of methods which either remove CO2 from the atmosphere one way or prevent it from being released at source. Now what you can see in this picture, it captures carbon dioxide and liquefies and put it to storage. Carbon capture and storage is a process in which a relative pure stream of carbon dioxide from industrial sources is separated, treated and transported to long-term storage, not even industrial storage, from atmospheric air. Now we'll have to, before we go into embark on how to do this, we'll have to have slight knowledge on GHGs, greenhouse gases as well, because that leads to global warming. Greenhouse effect, we know all about that. Greenhouse effect, the greenhouse gases restrict the radiation. It will re-radiate back to Earth and increase Earth's surface temperature. The greenhouse gases are water vapor, carbon dioxide, nitrous oxide, methane, ozone are primary GHGs. But in modern world, modern buildings, we use refrigerants. Refrigerants, we can remember way back in late 1920s, the older refrigerant like carbon dioxide, ammonia, probably ammonia is still using though, carbon dioxide, ammonia, those methyl chloride, those refrigerants were replaced by a very safe refrigerant called chlorofluorocarbon. But later we found this refrigerant attack our ozone layer and harmful UV rays hits Earth. Again, global warming increases and cancer producing effect. So finally, CFC refrigerants were banned and HCFC and HFC refrigerants became more popular. Now, this substance, HFC, means hydrofluorocarbons, were introduced to replace CFC refrigerants. Those are R23. 134 is very common refrigerant in our automobiles. And then air conditioners, 410, very lately we found 410, 407C is a drop-in refrigerant for R22, very common refrigerants. Unfortunately, now we can find these refrigerants have higher global warming potential. Now that is too bad because global warming increases. So we'll have to select refrigerant, first non-CFC and global warming potential 50 and below. That is the real target in green buildings, but we can't achieve that way. But lesser GWP. We have Kigali Amendment in Montreal Protocol. The phase down is happening now, and the path is there. I'm not going through these things. So one thing we should remember, in our buildings, we'll have to see what are the refrigerants in air conditioners, or sometimes we have heating systems in newer area, and rest of things air conditioning. The refrigerant should be low GWP. So global warming, the effects we can see at the moment. Ice caps are melting. On the other hand, El Nino effect, the bushfires, wildfires happening in concurrently, the other side of the world, flooding. All this is due to global warming. So we are trying to keep the global warming temperature below 2 degrees C. That is the Kigali Amendment does. So effects of net zero operational carbon, we'll have to mind the carbon emission will improve global warming. So we'll have to keep it 1.5 degrees C level. Now, before we discuss how really we embark on reducing operational carbon of a building, we'll see some case studies. I have taken one case study. I had two, but I omit that due to time constraints. This is Bawa Residence, Chennai. It's a storied residence building. Project area 330 square meters. Energy performance index is 0.77 kilowatt per hour per square meter per year. Architects, Midori Architects. MEP by Arul Designs, energy consultant, Quad Energy, and so forth. They have given passive strategies in this building. Ventilation is given prominence. They have found aerodynamic format in this building and twisted the building orientation by 12 degrees, as you can see, to capture wind. These design elements ensure a constant airflow of 0.625 meters per second, even with the outdoor wind velocities as low as 0.7. So they have assured they get enough wind and enters the atrium by passive strategies. Daylight. The residence has been deliberately designed with a central atrium, ensuring ample daylight in all regularly occupied areas. To optimize the natural light while minimizing glare, windows are strategically placed on 4 facades. Approximately 99% of the building experience illuminance levels exceeding 110 lux, quite adequate for a house. The building incorporate glasses. They are not using just normal glasses. With visible light transmission, VLT 42% and ULEV of 1.6 watt per square meter Kelvin. Also SHGC, that is solar heat gain coefficient, of 0.29. Now these values may be Greek to you. I will give an example. If you use a normal glass, single pane, a 6 millimeter thick glass, the ULEV, we are discussing what is ULEV. is the heat transmittance of the glass. How fast, how much it transfer heat energy into the building. So it has to be low. If the U factor is low, will be low. Now, heat transmittance, SI units watt per square meter Kelvin. Normal 6 millimeter glass, plain glass, has 5.9 watts per square meter Kelvin, almost 6 watts. Very, very high. But in Sri Lankan contest, we are in ASHRAE a climate zone 0. We must use glasses down to 3.6 watt per meter Kelvin if it is aluminium and operable. If it is aluminium and operable, maximum ULE should be 3.6, 6 watts per square meter Kelvin. You cannot use, you will not achieve green building status. Your energy consumption will be very high. Now see, in this, they have achieved, this is the ASHRAE a limitation, maximum 3.6 watt per meter Kelvin, but they have achieved 1.6 watt per square meter Kelvin. Now that is how we reach net zero status. Expensive, but we'll have to use. So some people have a misunderstanding. These green buildings and probably net zero buildings are very expensive to construct. Generally, a green building costs 20-25% above the normal building cost. But on the long run, that is service life of the building, you definitely achieve. Water management. Rainwater from all roofs and non-roof structures is collected for use and groundwater recharge. That is a requirement. Treated grey water is used landscape irrigation. Water efficient plumbing fixtures and flow regulators are used. Water metering is implemented to monitor usage. Materials used, approximately 33% of the materials have recycled content. 75% of the wood utilized as either rapidly renewable or certified by the Forest Stewardship Council, that is in India. 50% of the overall building materials are manufactured and sourced locally within 400 kilometers radius. See, that reduces embodied carbon. Then comes the heating, ventilating, and air conditioning system. Cooling load for the structure is 10,576 kilowatt hour per year. A variable refrigerant flow VRF system with R410 is used, and coefficient of performance of the refrigeration system, that is air conditioner, is 5.5 at part load and 4 COP4 at 100%. Now, to achieve energy saving, to comply green building, ASHRAE standard 90.1 energy efficiency standard gives the minimum efficiency we should have for VRF systems. Now that is, I have given here, as per ASHRAE 90.1, efficiency should be 11.3 kilowatt per ton, or in COP 3.3. See what they have done. They have achieved 4 at full load. And this is full load efficiency. So that is quite good. It is difficult and expensive to do that. Now we locally we buy, I will give you example. We buy things like DX split units. Efficiency, when you check, is 9 kilowatt per ton. The ER is 9 kilowatt per ton. Now we'll have to bring it to 11.3 EER. EER should be 11.3. Now I have to correct this. We don't call kilowatt per ton here. It is EER. So EER is the efficiency found this way. It is found this way. Refrigeration capacity in BTU per hour divided by power input, watts. BTU power over watts is EER. So what we say, EER of a equipment should be equal or higher than 11.3. Or COP, for that matter, 3.3. COP also efficiency. So this is used for COP. Energy efficient and the equipment that they use, all star labeled equipment. Now hot water needs are met using heat pumps, refrigeration. Efficiency 50 to 60% and COP is 3.6. The heat pumps produce cold air as a consequences of heating this. So that cold air water, this cold air pump, heat pump from the cold air is utilized to cool staircase area. Wonderful. See? ELV, the building incorporates energy efficient lighting fixtures and occupancy sensors. A home automation system is implemented featuring door and lock sensors, a video intercom system for visitor management, and gas leak detectors as well, because this is a VRF system. So like that, the project has net metering, allowing for seamless integration of renewable energy sources with the utility grid. Additionally, battery backup system with a capacity of 75 kilowatt installed, providing 2-day autonomy period in case of power outage. This ensures uninterrupted power supply and enhance the reliability of the energy systems. So we can now summarize and then learn how the net zero has come. Renewable sources. Solar panels have been installed. They are generating approximately 39.19 megawatt hours of renewable energy annually. They are on the terrace. The system comprises 62 solar panels with a capacity of 400 watt peak each panel, totaling 25 kilowatt peak. As a result, the project generates an excess of 5,803 kilowatt hour per year. So finally, annual energy consumption is 37 megawatt hours per year. Annual energy generation is 39, higher than the consumption. So annual energy generation kilowatt hours, megawatt hours, 39. So it is net zero. Right. So now we have to turn to building services engineers and their role to achieve this kind of an approach. Building services engineers' role, firstly, reduce building energy consumption, complying ASHRAE 90.1 will have to reduce energy consumption by utilizing better materials for walls, better materials for floor, windows, roof, and reduce heat gains. High efficient equipment with energy label. Everything used in the building should be energy labeled equipment. When you purchase a refrigerator, has to be super level, super grade, star labeled refrigerator, which utilize minimum energy. Simple example. Air conditioners will have to comply if it is EER or rather VRV system or DX systems, then energy efficiency ratio should be 11.3 and above. You can't use 9 EER. In Sri Lanka, most of the equipment we find, what is brought here is 9 EER or maximum 10. If it is chillers, yeah, that is COP, we'll discuss that, or kilowatt per ton. All HVAC equipment shall be compliant minimal energy standard values from 90.1. That we'll separately discuss. Next goal for engineers, achieve operational carbon reduction compliant benchmarks utilizing the above. If it is a new building, reduce embodied carbon compliant benchmarks. Finally, you'll have to reduce total energy use by 50%. That is a big task for building services engineers. Next, install renewable energy sources such as solar PV, wind energy, or geothermal energy offsetting total energy demand of the building. Install solar PV energy storage devices such as batteries for use during night. Now, when we just come to a HVAC equipment shall comply minimum energy standard and reduce 50%, how do we do this? We should run a model. A simple case, eSoft software can be used, a whole building energy simulation method, and we can find baseline building energy, kilowatt hours or megawatt hours per annum, and then we'll have to apply all the means to reduce at least 50% of that. That's how we really do it. Okay, we'll take reduction of embodied carbon. How do we do that? Reuse building materials is the main thing. In a renovation project, you usually save between 50 to 75% of embodied carbon emissions compared to a new building. Use reuse materials. Use low carbon concrete mixes. Concrete can be biggest source of embodied carbon for new site. Utilizing fly ash in concrete could achieve reduction in embodied carbon. Let's see how we do that. Use of less carbon intensive materials for buildings such as rammed earth, softwood timber, cross-laminated timber, stone, clay brick, whatever. Now, clay brick is our ancient Sri Lankan method. I think about 8 years ago, I put this clay brick into ASHRAE, one of the committee meetings. I tried to open their mind that we were using much more sustainable methods way before what sustainability word came in even. So this is an example. Use of reuse building materials. See, building blocks can be used. Steel can be used. Hardwood. Low carbon concrete mixes. Now, there's a building block material known as AAC, aerated autoclaved concrete. Those are very lightweight concrete. It was not available in Sri Lanka. I was very fortunate enough to participate in a building project in Sri Lanka. First time we used AAC. We had to import it from Thailand. During that time, we didn't have any manufacture. But now it is being manufactured in Sri Lanka. AAC, now available, very lightweight. What does it mean? Aerated, autoclaved. The block has holes in it. Holes filled with air. Air is an insulator. That will bring lightweight, but the strength complies. You can cut it very easily. These are the gains. I have given you a comparison here. AAC block, concrete block, and brick. Thermal conductivity of a brick 0.81 watt per meter Kelvin. Watt per meter Kelvin. Brick 0.81, concrete block 0.51, AAC 0.122, very low thermal conductivity. Actually, the thing that I learned from the building that I did, that is Ani Vilas from French company, is a very high level villas. Normally, we will not be able to hire this or rent these villas because very expensive. Per day, it is cost will be a villa about 200 to 250,000 rupees. But what I learned, I actually got afraid when I commissioned, because you don't need air conditioning when you use aerated autoclave concrete, plus the roof complying ASHRAE 90.1. I had about 8 inches thick insulation in the roof. So you don't need air conditioning, absolutely. So this is how we reduce operational carbon. And furthermore, low carbon thermal insulation materials, panels from hemp. You know what is hemp? It is different grade of hemp, not marijuana or this the thing. This is used for. Now this is being very popular now in other part of the world. It will definitely come to, but in Sri Lanka we have higher water vapor content and relative humidity. That will be a concern. Then other materials like a rammed earth being used as a very new concept. Then we need solar PV to offset total energy. No point having solar PV without batteries to store it. 550 watt solar panel, say 4 hours per day operation, provides 2 kilowatt hours. Just example. For a house with monthly energy demand of 300 kilowatt hours, 5 numbers panels would sufficient for 4 hours per day, clear sky. 24-hour operation, it is obvious that energy storing is essential, because in the night, we can't use solar panels unless otherwise you store energy. So you need batteries. Now you can see this installation with batteries. Solar PV energy storage system is a system that uses solar energy to generate electricity and store in batteries. It can be either off-grid, grid connected, or hybrid, whatever. Typical solar PV plus battery system consists of PV system and lithium-ion batteries, as shown in the photograph. So the next reduction of operational carbon will go step by step. Carbon footprint reduction methods are discussed in following slides. Basic approach is this: reduce building energy 0.1 ASHRAE, high efficient equipment usage. All the HVAC equipment shall be complying minimum efficiency standards. So these are the steps. Now, clearly listen, people have some misinterpretation.
It's 7 o'clock.
I was reading this, right, okay, anyway. We have a misconception here. Like when we use ASHRAE standards, because it is written in US, we cannot use in Sri Lanka because our weather, our Sri Lankan conditions is different. Now that is incorrect, wrong. That is wrong. Before I explain that, I will take CIBSE, Chartered Institute of Building Services Engineers, that is a UK arm of ASHRAE, if I say so. Building Services Engineers in UK, CIBSE, have handbooks, but they have categorically printed there, this is to be used in England and Wales. But ASHRAE standards are for entire world. How? The start is, now we need not to readjust ASHRAE data to fit to Sri Lanka. No, we don't need to do that. Why? ASHRAE has done something. Entire countries in the world is given a climate zone. Climate zone, group. There are groups where the countries are grouped into certain climate zones. First thing we should know, our country belongs to what climate zone. Then they have produced set of guidelines and the factors like U factors, R values, so many other things to fit into that particular climate zone. Not even that, even selecting of air conditioners for the particular climate zone is given. So don't be afraid to use ASHRAE standards. First target is find the climate zone of your country, apply U values for selection of building fabric. Building fabric means building envelope. Second, minimize ventilation load by using calculations to comply with ASHRAE standard. As we know, green buildings provide adequate ventilation for benefit of occupants. Health and well-being is a priority of engineers. Health and well-being is addressed in this ventilation standard ASHRAE, and we calculate how much we should supply outdoor air to a building, because the buildings are now energy tight. And obviously the buildings are very thermally tight too. So there is no infiltration, is reduced. So we need outdoor air to dilute carbon dioxide in the building, dilute odors, dilute volatile organic compounds inside the building. So when we bringing in outdoor air into a building, that consumes power. So this standard gives you how we should comply and how we should reduce energy. So what we do over and above, verify with simulations for the resultant RH of the design, whether it comply with ASHRAE standard 55. It says relative humidity inside the air-conditioned building should be 60% below. So we keep it 55 to 60%. If the relative humidity is above 60%, how do we find this? From the simulations. We'll have to take evasive action to reduce relative humidity below 60. Next, the areas of the building sometimes you find densely populated. If you take office building, obviously we have a meeting rooms, auditorium, these are called densely populated. How ASHRAE categorize this? 25 people per 100 square meters and above. 25 people per 100 square meters and above called densely populated areas. Now in those areas, we'll have to adopt demand control ventilation method to drop energy consumption. Drop energy consumption. Not even that, sometimes we'll have to use energy recovery. Fourth item is select equipment with minimum efficiency that we'll go through. Example, use of minimum efficiency for water chillers, commercial packages, VRF units, DX splits. Use of performance requirement for heat rejection equipment. What are the heat rejection equipments? Cooling towers. There's a cap. We can't just use cooling towers. Use of fan power limitation in air handling units and wherever. We can't take air handling unit with a fan, what is manufacturer given. We'll have to check whether it complies a fan power limitation. Thereby we reduce energy consumption. Then use of minimum duct and pipe thermal insulation are values. Finally, use of energy control strategies utilizing BMS. So we'll quickly take over. These are the ASHRAE standards that we use in doing net zero buildings and green buildings. ASHRAE 90.1 energy standard for buildings except low-rise residential buildings. Thermal environmental conditions for human occupancy are ASHRAE 55. Then ASHRAE 62.1 is ventilation for acceptable indoor air quality. Then standard for design of high performance green buildings 189.1 and BACnet. Let's see how we do this. This is how, I'm not showing entire world, but this part of the world, how world climate map looks like. Sri Lanka has given 2 zones, but actually we have 3 zones. The hindrance was we had only data available from Katunayaka. So World Meteorological Organization input data came from Katunayaka. Now we have got Colombo, Rakmalana, Jaffna, Kandy. So we should improve this later. As we can see, it is zone 0A for northern area and zone 1A for wet area. Thermal zones are given and the name also given: 0 extremely hot, 1 very hot, 2 hot, that kind of a things. So as example, Katunayaka is 0A. Katunayaka 0A. So climate zone 0A, then we can find all the tables and their values under 0A. As I told you, U value is so much important. What is U value? Is the rate of steady state heat flow. In SI units, it is heat in watts that flows to a 1 square meter area with 1 degree Celsius temperature difference. So your U values have to be low enough to achieve energy savings. Now this is a table for climate zone 0. You can see very well climate zone 0, climate zone 0, and this table gives building envelope requirements. There are 3 categories. One is insulation entirely about it, metal roofs and attic roofs, and they have different ULEs. 0.22, 0.23, 0.153 we'll have to achieve. By doing so, we'll have to comply the resistance R values are 4.4 for a concrete roof, metal building are 1.8 plus R 3.3 for fill cavity, and attic roofs are 6.7. Then only we can go to net zero level. Walls, we don't need anything. That is a good advantage because mass walls that we use, brick and blocks, complies no thermal insulation is required, but it has to be 3.29 and below. So floors, mass floors 1.8, that is concrete, steel 1.9, wood frame 1.5. So if we achieve these ULEs, that means we'll have to improve the ULEs by having layers, insulation, then we can reduce heat transfer and reduce energy consumption. I will just give a glance. This is the Sri Lankan, this column gives you Sri Lankan ULEs that we use in normal circumstances. And if you want a green building, this is what we should be using. Or it is a net zero building, we should use these values. For instance, concrete slab, 150 millimeter. Our ULE is 2.26, but it has to be dropped to 0.22 in a net zero building. How do we do that? Thermal insulation, air gap, whatever. So similarly, asbestos roofs, zinc alum roofs, walls, we are good. 1.84, requirement 3.2 already. Continuous air barrier is a system that other part of the world use, like in England, every house, every building has a continuous air barrier. That is, air barrier goes in the zone and it prevents infiltration of air. In Sri Lanka, we don't have, but I was fortunate enough to participate in a design. We had continuous air barrier in Star Garments building in Katnayaka. Cool roofs. Cool roofs are light colored roofs which reflects solar energy. But I can't fathom our roof manufacturers have multicolor roofs, red, green, blue. The last techno show, I met one of these manufacturers and told them, look, don't do this. Have silver color, white color roofs for energy efficiency. Let's see, will they follow that? Now you can see roof insulation above concrete block. To achieve 0A status, we need 6.5 inches thick insulation. Similarly, zinc alum sheet, we need 8 inches thick insulation for zinc alum. Now fenestration, that is windows, glasses. Remember I told you 6 watt per square meter Kelvin normal glass. But we'll have to drop it to 1.73. It is non-framing, non-metal framing, that is wood, or metal framing 2.7, metal framing operable 3.51. Usually we are at here. 6 watt per square meter Kelvin should be dropped to 3.5. So that is what we should be doing. You can't use normal glasses. Not even that. We will have to reduce solar heat gain coefficient, and then we'll have to reduce VLT over SHGC. What we do, we use low E glasses. What is low E glass? Low emissivity glass. Has two panes, and air inside. If this is outside, this is inside, you have a lamination on the outside surface. You can see exactly here. This is the outside pane, this is inside pane, and the inside lamination, which reflects energy, most of the energy on the UV rays. If something absorbed, that will also reflected. So most of the green buildings and maybe net zero buildings, you will have to have low E glasses. Permanent projections. See, we need to explain what is a permanent projection. Permanent projection, first story level. The projection factor should be 0.5. Other stories, PF should be 0.2. What is PF? PF is a awning length divided by the height. So the ground floor will have to achieve 0.5. That is, your SHGC multiplier become 0.67. What does it mean? Solar heat reduced down to 67% if you have this 0.5 factor. So all this is contributes to reduction up to 50%. Now, ASHRAE 90.1 gives you net zero buildings or whatever. You have particular type of air conditioners to be used. Now, I have used as zone 0 to 3B. They have given package terminal air conditioners, rooftop air conditioners, chill water systems, constant air volume, and variable air volume. Let's see. Residential buildings, definitely it has to be a package terminal, either split units or window type. Public assembly buildings, 11,000 square meters or below, we must use package rooftop. Now, this is one of the best air conditioners because this is factory tested, performance guaranteed. You don't have any local involvement, no gas charging, no piping, nothing. You give the power supply, connect the ductwork, supply return. You don't need fresh air ductwork. We don't need extract ductwork because that is built in here. The other advantage, this has an economizer built in. If the outdoor temperature drops below 24 degrees C, this will take care of outdoor air to cool the building. Probably night purge. We are just touching that later. Buildings, public assembly buildings larger than 11,000. We are supposed to use a single zone, constant volume air handling units, single zone, and cooling type chill water. See how nice. Again, retail and 2 floor levels for fever. Retail, that is shops, small offices, rooftop package. Now, in the pathway to reduction of energy, how to select chillers? Very quickly, I will show you. ASHRAE 90.1 gives this particular table to select chillers. Now say water-cooled chillers, 75 tons, 75 to 150, 150 to 300, so forth. Your efficiency is given in part A, part B. Part A is full load matrix. Part B is part load matrix. That is chillers running for full load, block load, we select this energy efficiency levels. If the chillers are running for part load, we use this, or we'll have to use both combined. Let's say 300 tons, your efficiency at full load should be 0.66 kilowatt per ton. Part load 0.540 kilowatt per ton. That is the minimum efficiencies. If you can have further smaller values, the better. So when we are selecting chillers, we don't haphazardly select a chiller for the price, for the make, for the physical size, the weight. No. The efficiency. I'm going to give you a very quickly example. This is a case study. Ceylan Towers. You know all Ceylan Towers where it is? Just opposite a cinnamon hotels in the Gold Road. Ceylan Towers built in 1994. It so happened I designed the system, and then it was installed by a Danish company. They had done ambush chillers, and the efficiency, the highest efficiency during that time, a 0.83 kilowatt per ton. Actually, this is just after the Achillan Tower twin buildings, World Trade Center, and they had 0.83 kilowatt per ton. That is the highest efficiency during 1993 and 4. I have a study here, January 2012 to December 2012. This is the kilowatt hours per month, total kilowatt hours, annual energy consumption, 4.5 million kilowatt hours. Now, if we convert this to a carbon emissions, you'll have to use the carbon factor. Now, we have a problem here. We have diesel plus coal. So we have a combination. Factor is 5.835 into 10 to the power minus 4. When you multiplied 5.835 10 to the power minus 4 into annual power consumption, you get carbon emissions in metric tons. 2,645 metric tons of carbon dioxide. So that is the carbon footprint of the building, 2,645 metric tons. Now, 2015, they replaced with a magnetic bearing chiller, plus with a dedicated BMS, building management system, with energy saving strategies. See what happened. The total annual power consumption now 3.1 million. Earlier, what it was? 4.5 million. Now it is 3.1 million. CO2 emission is 1,893, 31% saving. So we call carbon footprint reduction 31%. This is what we can do with highest energy efficient equipment plus BMS. So quickly go through. These are the performance values required. Minimum efficiency for split units, larger split units, 12, that is 11.2 ER. The other one also 11.2 ER. And VRV, again 11.2 ER is the energy efficiency. Then cooling towers has a performance requirement, that is, you can see here, a 40.2 GPM per horsepower or above. What does it mean? I have a little example. This is a cooling tower which we selected for a project. The cooling tower, a water flow rate is 320 cubic meters per hour and fan motor output is 22 kilowatts. So if you put it to this format, A cooling tower water rate 320 cubic meters per hour becomes 1400 GPM. 22 kilowatts become 29 horsepower. Final result is 47.8 GPM, well above 40. So this complies the requirement for the cooling towers. We are supposed to have a multiple fan with a VFD. If the fan motor 5 horsepower and above, we must have VFD with some temperature controlling to reduce power consumption. And HUs, you have power limitation. It is given as supply air CFM multiplied by 0.0154 for variable volume, constant volume, supply CFM into 0.0011. That value should be equal to your horsepower. What does it mean? I have another example here. This is a HU selection. This is a HU selection. What we need is airflow. Now the airflow is liters per second, 3000 liters per second, and motor power is 5.5. So we convert that 3000 liters per second is become 6400 CFM, horsepower 7.1. So our factor, our horsepower should be 7.3. So already matching 7.1. Selection is 7.3 rather. So we are complying. That kind of a thing we'll have to do to reduce energy. So finally, building management systems, how to reduce to comply a higher energy efficiency and go to net zero building status. Now, we know we use BMS. Unfortunately, we use for just monitoring purposes. No, we have certain energy conservation measures through BMS. These are chill water reset, fan cycling, duty cycling, optimum start-stop, unoccupied, that is night purge, electrical demand limiting. All of these bring about massive savings. We'll take an instant picture. Now this is the BMS output screen. I took it on a very sunny day, time almost 2 o'clock, where it is Ceylon Towers. Now, originally we had, as far as I can remember, 350 into 350, 2 chillers were working together, but not 700, maybe 600 tons. But 2015 replaced chiller with a magnetic bearing oil-free compressor chiller, 400 ton. 400 tons chiller is working now for the entire building. But the great thing is at 2 o'clock, hot sunny day, the chiller is loaded only 71%. Thanks to BMS. Lot of strategies have put into operation. I'll give you some of these, not all that is implemented at Ceylon Towers, but say first one is chill water reset. Chill water reset is heavily misused in Sri Lanka, heavily misused, because chill water reset gives energy reduction instantly. So what happens is, if this is get to know by the GM of the hotel, he always do the chill water reset by himself. Chiller outlet temperature is 7 degrees C, return 12. Chill water reset is during part load operation, we raise the temperature 7 to 8, probably 8 to 9. But surely it is under part load, that is during night, a rainy day. So we'll have to find whether building operates on a part load. So we need the BMS system. The important thing, each degree of chill water reset reduces chiller energy cost by 1.5%. This is massive. But unfortunately, in Sri Lanka, all our people, they misuse this. They put it to 10 degrees C, and there are condensation issues. Humidity is high. Then they turn back to the designer. They turn back to the installer. Big problems. Now, this has to be used in part load, significant energy ASHRAE standard. Any system above 88 kilowatt hour has need resetting. Next one is fan cycling. This is used for constant volume fan systems where fans are continuously working throughout the occupied time. No, we should have some means of reducing and fan cycling. Instead of one fan, you can have a couple of fans, and we can cycle fans during part load. Even fan cycling option can be used for a car park. Many jet fans are installed. We can cycle 50 cars in a car park. But you have only 10 cars occupying. You don't need to run all the fans. Simple as that. Third one is duty cycling. Duty cycling to avoid setting unnecessarily electrical demand. That is why synchronous equipment starts. This will keep a time delays and cycle. The chiller that is operated today as the lead chiller, tomorrow it goes for lagging chiller. Everything is done by duty cycling. Optimum start-stop is a very vital thing. Optimum start-stop strategy can lower utility costs by reducing the operating time of HVAC equipment. The control system specified BMS must capable of monitoring, controlling the entire HVAC system. The control system should be capable of learning from the previous building operation. Now, in what we have done here, in the the BMS people have done there, a building operation usually 8 a.m. to 5 p.m. During Mondays, they start the chiller 6 p.m. and maybe 4:30 they stop. You would think waste of energy. No, 6 to 8 unoccupied will absorb coolness to the building, pre-cooling. That will offset the load. Monday 6, Tuesday maybe 7, Wednesday 7:30, Thursday 8. When you analyze entire week energy, kilowatt hours, is dramatically reduced by cooling the building compared to 8 to 5 complete week. So this is one way of optimizing. So optimum stop is in the ASHRAE standard that is given for 5,000 liters per second air supply and above. We'll have to use. Then the night purge. Night purge, you'll have to have HU and pre-design that. What it does, we use outdoor air when the outdoor air temperature below 24 degrees, used to cool the building during night. Predetermined time, both exhaust and fresh air dampers open. Only fresh air system operates to cool the building. Fresh air comes and circulates through the supply ductwork. Return comes and not recirculate, it will extract. Now, with the rooftop package units, this is built in. You don't need anything. You don't need a BMS. That has a economizer that will do automatically. Finally, electrical demand limiting. This is a fantastic BMS control strategy for energy conservation. I'm very unhappy because most of the building BMS contractors never do these things. What it does, a good way to lower electricity utility bills may be adopt an electrical demand limiting control strategy that restricts the HVAC demand. What happens? See, our demand now going up. Can you see? Now you are going up. but our energy cap is here. We can't go above. When the energy consumption reach the demand charges, demand value, BMS send a signal to all the DDCs where HU set point. Set point. What is point? Normally 24 degrees C dry bulb. To increase to 25 degrees C. What will happen? All the chillers will unload instantly. And this will not shoot up. This will not shoot up. It will go like this. So we discussed so many things to contribute to net zero and operational carbon reductions. So finally, achieving net zero buildings should be designed firstly to significantly reduce energy consumption, achieve 50% energy savings, use recycled low carbon materials, reduce thermal loads, operational loads, and carbon footprint of the building, use renewable energy sources, store energy for when renewable resources are reducing. Total energy consumption should be equal or reduced to energy produced in the building. So that is how we achieve net zero buildings. Hope you have understood all this. If you have any questions, we can discuss. Thank you.
Thank you, Engineer Dalugoda. It seems a very useful webinar and useful discussion. I have one question. The question is, what are the guidelines which have been implemented in Sri Lanka to achieve these requirements? I mean, the zero building, zero energy building concept.
Yeah. As I told you, it is actually standard 90.1 energy efficiency, the code that is heavily used for selecting equipment, selecting U values and R values to reduce envelope heat gains, and then thereafter ASHRAE 62.1 acceptable indoor environment and quality that is being used. ASHRAE 55 is used. These are things that we use in Sri Lanka.
Okay, these are the questions I got from the audience. It seems there are no any other questions from the audience. So, if so, we can. It seems we can wind up the session. I think we can go for the vote of thanks.
Yeah. Thank you, Engineer Asanka. First of all, I think I would express my appreciation to Engineer Chandana Dalugoda, who is delivered the informative lecture on this particular area. Thank you, Engineer Dalugoda, for your excellent effort to enhance our knowledge. Secondly, I would extend my appreciation to ISL staff members and technical team arranging facilities for this particular event. Then, on behalf of the Building Services Committee, I would say that all the participants, thank for your presence. And again, Engineer Isuru and Engineer Kaushalya and the webinar team, thank you your effort to succeed this event. Then we are going to wind up the session. So again, all of the participants, thank you for your presence. Good night all to you. Thank you.